All right, pressing on to section 7.3. This is using the central limit theorem. So this is going to be just more examples. So what you saw in the previous section was, learning and understanding what we mean when we talk about the sampling distribution of the mean, that this is a distribution of sample means. So you take a bunch of samples, you collect the means of each of those samples, and when you plot each of those sample means on a dot plot, that itself creates a distribution. And that distribution is normally distributed. That distribution will have its own mean, its own average. So it's a mean of means that will be equal to the population mean. The standard deviation of the distribution of means will be the standard deviation of the population divided by the square root of the sample size. The standard deviation of the sampling distribution of the mean is also called the standard error of the mean. And this is how you can calculate it separately. This is the same fraction that's used up here, okay, to describe the standard deviation for this distribution. And for z-score, I guess, might be almost better to think of it as writing it like this. All right, so the z-score related to the distribution of sample means is equal to a given mean minus the mean of the distribution of sample means divided by the standard deviation or the distribution of sample means. And you'll notice that if we take this value and we substitute in place of that value this fraction, then that's what you get here in the denominator. And if we take this relationship between the mean of the distribution of sample means and we use that as what's called a point estimate for the population mean, then actually these two quantities are equal. So if we take this value here and we substitute for it the population mean, then we get this value here in the numerator. Okay. So the relationship with a z-score is still the same. It's just you can change some of the variables in the z-score equation to relate to different distributions. Okay. So again, we're going to be looking at some other examples using this. So this was, here, this was a concept I think I talked about during one of the examples in section 7.1, but here's kind of like a formal picture of this idea. So, if we were looking at maybe the weight of black bears in California, then the weights of black bears in California could be normally distributed. Okay, now if the weights of the population of all bears in California is normally distributed, Then we could go throughout the state of California and we could collect samples. So what I mean is we could trap, maybe 16 bears in different locations and measure their weights. And from 16 bear weights, we end up calculating an average or a mean of that sample of 16 bears. Then we go to another location. We calculate the mean of another 16 bears in another location. And then we go to maybe a third location. We trap 16 bears. We measure their weight, and that becomes a mean of that third sample of black bears. And we just keep going, keep going, keep going, and collect a whole bunch of sample means that way. And if we take each of those sample means and we graph them, then the distribution of those sample means will be normal. So this will be a normal distribution. And what do we mean by normal? We mean that it is a symmetrical shape. The data takes a symmetrical shape, and it's also bell-shaped. And because of those things, we could also apply the empirical rule to it. Now, that's if we kind of were to follow, this path down to graphing the distribution of sample means in order to come up with a normal curve. But the distribution of the weight of all black bears in California, of the population of black bears in California, didn't have to be normal. It could have been uniform. So there were as many bears of a low weight as there were a high weight, as there were kind of like in a middle weight. Okay, the shape of that distribution of bear weights was flat. It was uniform. And if we had gone through the state of California and collected samples, taken the mean of each sample, and then graphed it, that too would have given us a normal distribution of averages, a normal distribution of means, even though the population distribution was uniform. The shape of the distribution of means would have been normal. And again, if the distribution of weights of black bears in California hadn't been normal or uniform, but it had been exponential, and we went through to different places and sampled 16 bears and took all of those average weights from each of those trappings, each of those samples, and we were to graph those means, again, we would have gotten a normal distribution of sample means, even though the population distribution of weight was exponential to start with. So regardless of the shape of the distribution of the random variable at the beginning for the population, when we take samples and we calculate the mean of each sample, and we graph the means of those samples, we'll always end up with a normal distribution of sample means. And again, that means that the shape of these means is symmetrical and that it's bell-shaped. And again, I like to refer to it as the distribution of sample means. And that's kind of what I call capital X bar. But other textbooks will instead call it the sampling distribution of the mean. Okay, so to me, this makes a little more sense, but this does, a little bit too. But just be aware if you see the more textbook um, uh, definition of capital X bar, that's what it is. All right. So we'll look at an example here next, but I just wanted to kind of talk about, this relationship. Um, and the central limit theorem, says that the center of this distribution here, which is the mean of sample means, which is the average of all of these sample means, that will be equal to the mean of the random variable for the entire population. Okay, so let's go ahead and stop it here. Let me know if you have any questions, and we'll move on to doing an example next.